What is a power supply module? How does it function and its application? A power supply module is an electronic device designed to convert electrical energy from one form to another and provide power to other electronic devices or systems. It serves as the intermediary between a power source, such as a mains outlet, battery, or solar panel, and the load, devices or systems that require power. Key functions of a power supply module: voltage conversion and power supply modules. Voltage conversion is the process of transforming electrical voltage from one level to another to meet the requirements of a connected device or system. This can involve stepping up, increasing, or stepping down, decreasing the voltage, depending on the application. Types of voltage conversion. Step-down conversion, buck, reduces a higher input voltage to a lower output voltage. Commonly used in chargers and devices requiring low operating voltage. Example: converting 12V DC to 5V DC for USB devices. Step-up conversion, boost, increases a lower input voltage to a higher output voltage. Used in applications like LED drivers or systems needing higher operational voltage. Example: boosting 3.7V from a lithium battery to 12V for powering devices. AC to DC conversion, converts alternating current, AC, to direct current, DC, using a transformer, rectifiers, and filters. Used in most consumer electronics and industrial devices. Example: laptop power adapters converting 230V AC to 19V DC. DC to AC conversion, inversion, converts DC to AC for devices requiring alternating current. Used in renewable energy systems, such as inverters for solar panels. Example: converting 12V DC from a car battery to 110V/230V AC for appliances. AC to AC conversion changes the voltage of an AC signal using transformers. Common in power distribution systems. Example: stepping down 230V AC to 110V AC for devices designed for lower voltage regions. DC to DC conversion changes one DC voltage level to another using switching or linear regulators. Compact and highly efficient, often used in portable electronics. Example: converting 12V DC from a car battery to 5V DC for charging phones. Components involved in voltage conversion. Transformers change the AC voltage level by electromagnetic induction. Used in AC to AC and AC to DC converters. Rectifiers convert AC to DC by allowing current flow in one direction. Used in AC to DC power supplies. Switching regulators use high-frequency switching to step up or step down voltage efficiently. Found in SMPS and DC-DC converters. Linear regulators reduce voltage by dissipating excess power as heat. Provide smooth and stable output, but are less efficient than switching regulators. Filters, capacitors, and inductor smooth out ripples and noise to ensure clean and stable output voltage. Applications of voltage conversion. Consumer electronics, charging phones, AC to DC, and powering USB devices, DC to DC. Renewable energy systems, solar inverters, DC to AC, and charge controllers, DC to DC. Automotive systems, boosting battery voltage, DC to DC, and powering in-car appliances. Industrial equipment, powering heavy machinery, AC to DC or DC to DC. Telecommunications, ensuring stable power for network infrastructure, AC to DC and DC to DC. Voltage conversion ensures compatibility between power sources and devices, enabling efficient energy use across a wide range of applications. Current regulation and power supply modules. Current regulation is the process of maintaining a stable and controlled flow of electric current to a load, regardless of variations in input power, load conditions, or environmental factors. This ensures that the connected devices operate safely and efficiently. How current regulation works. A power supply module achieves current regulation using a combination of components and control systems. Feedback mechanism monitors the current flow to the load and adjusts the power output to maintain a constant current. Uses sensors or shunt resistors to measure current and compare it to the desired level. Current limiting circuits protects the power supply and the load from excessive current by restricting it to a predefined maximum level. Automatically reduces output voltage or shuts down the supply if the current exceeds safe limits. Active regulation components. Linear regulators provide smooth and stable current but dissipate excess power as heat. Switching regulators control current efficiently by adjusting the duty cycle of a high-frequency switch. Pulse width modulation, PWM, used in switching regulators to dynamically adjust output current while maintaining efficiency. Types of current regulation. Constant current regulation, CC, delivers a steady current regardless of changes in load resistance or input voltage. Used in applications where precise current control is critical. Example, LED drivers, battery charging circuits. Current limiting protects against overcurrent situations by capping the maximum current. Example, power supplies for sensitive electronic circuits. Dynamic current adjustment adjusts the output current based on the load's requirements, often seen in programmable power supplies. Applications of current regulation. Battery charging ensures controlled current flow during charging to prevent overcharging or overheating. Example, lithium-ion battery chargers with constant current/constant voltage, CC/CV, profiles. LED lighting supplies a constant current to LEDs to ensure uniform brightness and prevent damage from overcurrent. Example, LED drivers and lighting systems. Motor control regulates current to maintain torque and prevent overheating in electric motors. Example, power supplies for robotics and industrial automation. Telecommunications equipment maintains stable current to power-sensitive networking hardware. Example, backup power supplies in data centers. Medical devices provides precise and stable current for devices like imaging systems and patient monitors. Example, current-regulated supplies for MRI machines. Consumer electronics protects devices like smartphones and laptops from overcurrent during operation or charging. Example, USB chargers with built-in current regulation. Benefits of current regulation. Device protection prevents damage from overcurrent conditions. Improved performance ensures consistent performance of devices that require precise current control. Energy efficiency minimizes power waste by delivering only the required current. System reliability reduces the risk of overheating and failure, extending the lifespan of both the power supply and connected devices. Current regulation is a critical function in power supply modules, ensuring safety, efficiency, and reliability across a wide range of applications. Filtering and noise suppression in power supply modules. Filtering and noise suppression are essential functions in power supply modules that ensure the output voltage and current are clean and stable. This involves removing unwanted electrical noise, harmonics, and ripple that can interfere with the operation of connected devices. Why filtering and noise suppression are needed. Electrical noise sources. Power line interference. Switching transients in the power supply. Electromagnetic interference, EMI, from nearby devices. Effects of noise. Disruption of sensitive electronics. Reduced performance in communication systems. Errors in analog and digital circuits. Audible humming in audio equipment. Key components for filtering and noise suppression. Capacitors filter out high-frequency noise and smooth DC output. Placed across the output or between the power lines, bypass capacitors. Inductors choke, block high-frequency noise while allowing low-frequency signals or DC to pass. Used in combination with capacitors in LC filters. Resistors work with capacitors and RC filters to dampen noise and prevent oscillations. Transformers provide isolation and reduce conducted noise between the input and output. Ferrite beads suppress high-frequency noise in power lines and signal wires, commonly used in USB cables and power cords. EMI filters, special filters designed to suppress electromagnetic interference, typically include inductors, capacitors, and resistors. Techniques for filtering and noise suppression. Low-pass filters allow low-frequency signals, or DC, to pass while attenuating high-frequency noise. Example, capacitor filters in DC power supplies. High-pass filters used to block low-frequency noise in specific applications. LC and RC filters, combination of inductors, capacitors, and resistors for advanced noise filtering. Shielding and grounding, physical barriers, metal shields, and proper grounding reduce EMI and radiated noise. Snubber circuits, absorb voltage spikes caused by switching transients, especially in SMPS. PFC, power factor correction, improves power quality by reducing harmonics and ripple at the input stage. Applications of filtering and noise suppression. Consumer electronics, ensures clear audio and video signals in TVs, speakers, and home theaters. Medical equipment, reduces noise to prevent interference with sensitive devices like ECG monitors or imaging systems. Communication systems, eliminates noise that could disrupt data transmission in routers and modems. Industrial automation, prevents errors in sensors and control systems caused by electrical noise. Automotive systems, filters noise from alternators and other components to protect onboard electronics. Renewable energy systems, reduces noise from inverters and converters for efficient energy transfer. Benefits of filtering and noise suppression. Improved performance, ensures that connected devices operate without disruptions. Protection, safeguards sensitive equipment from noise-induced damage. Compliance, helps meet electromagnetic compatibility, EMC, standards. Enhanced reliability, reduces wear and tear on components caused by voltage fluctuations. Filtering and noise suppression are indispensable for maintaining the stability and efficiency of power supplies in diverse applications. Overload and short-circuit protection in power supply modules. Overload and short-circuit protection are safety mechanisms built into power supply modules to prevent damage to the power supply, connected devices, and wiring in the event of excessive current or a short circuit. These features are crucial for ensuring safe and reliable operation. 1. Overload protection. Definition. Overload protection limits the current drawn by the load to a safe level when the current exceeds the power supply's rated capacity. This protects the system from overheating, damage, or failure. How it works. Current sensing. The power supply monitors the current using a shunt resistor, current transformer, or similar sensing mechanism. Control response. If the current exceeds a predefined threshold, the module reduces the output current or shuts down completely. Reset mechanism. Protection may be automatic, resumes normal operation when the overload is removed, or manual, requires user intervention to reset. Types of overload protection. Fold back current limiting. Reduces the output current and voltage to a safe, low level under overload conditions. Constant current limiting. Maintains a fixed current output while reducing voltage during overload. Overtemperature shutdown. Turns off the power supply if an overload causes the internal temperature to rise excessively. 2. Short-circuit protection. Definition. Short-circuit protection prevents damage when a direct connection, short circuit, occurs between the power supply's output terminals, causing an abrupt increase in current. How it works. Rapid detection. The power supply detects the high current spike caused by the short circuit. Immediate action. It either reduces the output current to a safe level or shuts down to prevent damage. Reset mechanism. Similar to overload protection, short-circuit protection can be automatic or manual. Techniques used in short-circuit protection. Current limiting. Caps the output current to a maximum safe value. Electronic crowbar. Activates a fast-acting switch, e.g., SCR or relay, to short the supply internally, protecting downstream components. Fuses or circuit breakers. Disconnects the power supply physically when the current exceeds a critical threshold. Key components for protection. Shunt resistors. Measure the current for overload or short circuit detection. Thermal sensors. Monitor the temperature for over-temperature conditions caused by overload. Transistors or MOSFETs. Act as switches to limit or cut off current flow. Fuses. Sacrificial components that blow under excessive current, requiring replacement. Relays. Mechanically disconnect the circuit during a fault condition. Applications of overload and short-circuit protection. Consumer electronics. Protects chargers, televisions, and laptops from power surges or internal faults. Industrial systems. Safeguards machinery and control systems from damage due to electrical faults. Medical equipment prevents critical devices like ventilators and monitors from malfunctioning due to electrical issues. Automotive systems protects onboard electronics from wiring faults or component failures. Renewable energy systems prevents damage to inverters, batteries, and solar charge controllers during faults. Telecommunication equipment ensures uninterrupted operation by protecting sensitive hardware from overloads. Benefits of overload and short-circuit protection. Device safety prevents overheating, fires, and damage to power supplies and connected devices. System reliability maintains stability and prolongs the lifespan of the power supply and devices. User protection reduces the risk of electrical hazards. Compliance meets safety and regulatory standards such as IEC and UL certifications. Overload and short-circuit protection are indispensable for modern power supplies, ensuring safe operation across a wide range of applications and environments. Power efficiency in power supply modules. Power efficiency is the ratio of useful output power to the total input power, expressed as a percentage. It indicates how effectively a power supply converts input energy into usable output while minimizing energy loss as heat or other forms. Efficiency formula. Efficiency eta equals output power, input power, times 100%. Efficiency eta sad face, input power, output power, times 100%. Output power, the power delivered to the load. Input power, the total power drawn from the source. For example, if a power supply delivers 90 watts to a load while drawing 100 watts from the mains, its efficiency is. Factors affecting power efficiency. Design type. Linear power supplies, typically less efficient, 50-60%, due to energy dissipation as heat. Switching power supplies, SMPS, highly efficient, 80-95%, due to the use of high-frequency switching techniques. Load conditions. Efficiency varies with the load. Power supplies are often most efficient at 50-75% of their rated load. Component quality. High-quality components, e.g., low-resistance MOSFETs, efficient transformers, reduce energy losses. Thermal management. Poor heat dissipation leads to increased losses, reducing efficiency. Input voltage and frequency. Variations in input conditions can impact conversion efficiency. Improving power efficiency. Use of high-efficiency topologies. Switching regulators, buck boost, are more efficient than linear designs. Power factor correction, PFC, reduces reactive power losses, improving overall efficiency and compliance with regulatory standards. High-frequency operation reduces the size and losses in transformers and inductors. Low-loss components. Use of components like silicon carbide, SiC, or gallium nitride, GaN, transistors. Thermal design. Efficient cooling systems, e.g., heat sinks, fans, prevent overheating and improve performance. Load matching. Ensuring the power supply operates near its optimal load conditions. Applications where efficiency is critical. Data centers. High-efficiency power supplies reduce energy costs and heat generation in large-scale operations. Renewable energy systems ensures minimal loss of energy harvested from solar panels or wind turbines. Portable electronics increases battery life by minimizing power losses in converters. Electric vehicles, EV, enhances range and reduces energy waste in onboard charging systems. Industrial automation reduces operational costs and energy consumption in factories. Advantages of high power efficiency. Energy savings. Reduces electricity bills and conserves energy resources. Reduced heat generation. Minimizes cooling requirements, enhancing reliability and longevity of components. Environmental benefits. Lowers carbon footprint by reducing energy waste. Regulatory compliance. Meets efficiency standards like Energy Star, 80+, or EU Eco-Design requirements. Enhanced performance. Provides consistent and reliable power to critical systems. Power efficiency is a key metric in power supply design, ensuring optimal performance, cost savings, and sustainability across a wide range of applications. Applications of power supply modules. Consumer electronics, powering devices like televisions, smartphones, laptops, gaming consoles, and home appliances. Example, USB chargers for mobile phones or adapters for laptops. Industrial automation, powering machinery, robotic systems, sensors, and programmable logic controllers, PLCs. Example, SMPS used in automated assembly lines. Medical equipment, providing precise and stable power for sensitive medical devices like MRI machines, ventilators, patient monitors, and surgical tools. Example, isolated power supplies ensure safety in critical medical environments. Telecommunications, powering communication infrastructure such as base stations, routers, switches, and data centers. Example, DC-DC converters and cellular towers for signal processing equipment. Renewable energy systems, managing and converting energy from solar panels, wind turbines, or other renewable sources. Example, inverters for converting solar DC power to usable AC for home or grid use. Automotive and transportation, powering infotainment systems, lighting, sensors, and electric vehicle (EV) components. Example, DC-DC converters for regulating voltage in electric and hybrid vehicles. Aerospace and defense, used in avionics, radar systems, communication equipment, and control systems. Example, rugged power supplies designed to withstand harsh conditions in aircraft and military vehicles. Data centers and computing, supplying power to servers, storage devices, and networking equipment with high reliability. Example, redundant power supplies in server racks to ensure uninterrupted operation. Research and development, used in labs to test and develop new technologies, circuits, and prototypes. Example, programmable power supplies for experiments and precision testing. Lighting systems, powering LED lights and display systems in homes, businesses, and public spaces. Example, drivers for LED strip lighting. Portable devices, charging and operating portable electronics like cameras, power banks, and drones. Example, battery management systems, BMS, in portable chargers. Security systems, powering surveillance cameras, alarm systems, and access control devices. Example, backup power supplies for continuous operation during outages. Uninterruptible power supply, UPF, providing emergency power for critical systems like computers, medical devices, and industrial machines. Example, UPS systems in hospitals and financial institutions. Household and commercial appliances, operating washing machines, refrigerators, microwave ovens, and HVAC systems. Example, SMPS in smart appliances for efficient power management. Power supply modules are integral to nearly every aspect of modern technology, ensuring reliable, efficient, and safe power delivery.